All right, video number 2. Um, so again, we went through a couple of examples of integration by parts, and this particular example, we had to do 2 integration by parts in order to get this final answer. But again, the question I posed at the end of the last video was, what if this was a t to the 7th? That would take 7 different integration by parts to do this. Well, there's a shorter way to do it, and here it is. So there is an easier method. Um, the idea is we can use this thing which is called tabular integration. If one of the function's derivatives terminates, and the other one is a cyclical function, meaning that its derivatives or antiderivatives eventually will cycle back to the original function in some form or another. Now the coefficients don't really matter, but as long as the actual main function cycles back to its original within a certain number of cycles, then that is a cyclical function. So something like sine of x or cosine of x, if you take the derivative of sine of x 4 times, you're going to end up right back at sine of x. If you take the antiderivative or the derivative of an exponential function, it keeps giving you the same function over and over again, or at least the same base function. Again, the coefficients and things don't matter. Um, so let's take a look at how this works and how this would make the problem that we took up here a little bit easier. So we already decided our u. Our u was, the original u was t squared, and our dv was e to the t dt. So t squared and e to the t dt. So what we've got here is we've got this little table. This is our u value, so that was t squared. And really what this is going to start off with, this is our dv. We're going to start off with here. Should probably put a d there. This is e to the t. And the idea is this side we're going to take derivatives until it terminates, and you'll see what I mean. This side we're going to keep taking antiderivatives until we get to the part where this one terminated. So we start with the left. Take derivatives. So the derivative of t squared is 2t. The derivative of 2t is 2. And the derivative of 2 is 0. Now every derivative from here on is going to be 0, right? Because the derivative of 0 is 0. So this is what I mean by it terminates. It gets to 0, and then all the derivatives from there on are 0. So we stop there. Over here, we're going to match these rows with the antiderivatives of e to the t, since this is our dv column. So the antiderivative, of course, of e to the t is e to the t. The antiderivative of e to the t is, again, e to the t, and so on. But I'm going to stop here because I've matched now the 0. This is what's going to make things easier, because now I start here with t squared, and I match it up with this one and multiply. Then I go to the 2t, and I match it up with this one and multiply. Then I match this 2 up with this e to the t and multiply. So it's a diagonal here. And then, excuse me, this 0, obviously there would be another e to the t down here, but the 0 times e to the t would just start canceling everything out because it's all 0. So the one major thing you have to understand here, and I want to make sure you guys get this, is that this one right here will keep its sign. Whatever these things were, this could have been negatives or positives, it doesn't matter. But this is going to keep its sign. So when I put a plus there, it doesn't mean this has to be positive. It just means it's going to keep whatever the sign is. This one right here, the next one down, is going to change its sign. Again, does not necessarily mean it has to be negative. It just means whatever you get when you multiply these, you're going to change the sign. Then this one is going to keep its sign, and that pattern alternates all the way down. So it always starts with keep, change, keep, change, keep, change. It always goes in that pattern. So you always start with keep, and then it alternates. So ultimately, the antiderivative of what we had up in the top here is going to be t squared e to the t. That's from this one. Change the sign here, so this is going to be minus 2t e to the t. And then keep the sign of this one, which is going to be 2t plus c. And what you should recognize is that this is exactly the same as what we had here. This is what is called tabular integration. It's called tabular simply because this is a table. So you're making a table. So this works, again, really well if you have one derivative which terminates, which this one did, and one derivative which is cyclical, which in this case exponentials are. So exponential, sine, cosine, those are cyclical functions. Easiest ones to do that with. And this side must have some kind of a terminating derivative. Yeah, I think you can actually technically do this without, but it's a lot more challenging to do. This is the easiest method. So again, only use tabular when you have that circumstance. Otherwise, just go with the standard integration by parts. Okay. Next example. So now we're going to have the integral of e to the x sine of x dx. Now, the biggest thing with this one is that both of these are cyclical functions. So we cannot use tabular integration because the derivative of e to the x is going to keep being e to the x. The antiderivative of sine of x is going to cycle every 4 times back to sine of the x. Or if you flipped them, it would be the same basic idea. So that's not going to work. It's a little bit of a pain to do this one, but you'll see hopefully in the end what you're looking for and how it works. So let's go with our standard integration by parts, which says that my u value should be, let's see, L, no logs, I, no inverse trig, P, no power functions, E, exponential. So that means this one is my u value. So u equals e to the x, which means dv is everything left, which is sine x dx. Okay, I'm going to need du, which is the derivative of this one, which fortunately is just e to the x dx. Here, this is the antiderivative, so I'm going to need v, which is the antiderivative of sine, which is negative cosine x. And now we're going to go ahead and follow our pattern, which says u times v minus the integral of v du. So this thing is going to equal u times v, which is negative e to the x cosine x minus the integral of v du, which is going to be the negative of e to the x cosine x dx. Okay, this negative can make a positive. Okay, this step is not essential, but it just cleans it up a little bit. Okay, so now I got to look and try and figure out this integral. What you should see is now I've got an exponential, another trig. So we're going to have to do another integration by parts. So, should follow the same basic idea. U is once again going to be e to the x. And that means dv is everything left, which is cosine x dx. So du is e to the x dx. Antiderivative over here, v, is going to be sine x. Oops, no dx. Took the antiderivative, dx is gone. All right, so now let's go ahead and rewrite it. Now remember, this first part stays. So that's going to be negative e to the x cosine x. Now this part right here is what I am taking the new integration by parts on. So it's uv, so that's e to the x sine x, minus the integral of v du, so that's minus integral e to the x sine x dx. So we've got an exponential and a trig, so it looks like we would have to do it again. Well, hopefully you can figure out at this point that if we keep doing this, we're going to end up with one that looks like this every single time. So literally you could do this infinitely and never really come up with the answer. This is what you have to recognize. Whoops. All of this right here is what we're trying to integrate. So this integral of e to the x sine of x dx equals this. But I really haven't solved for this integral because I have another integral in it. What you should notice, however, is that this integral is the same as this integral. So what that means is I'm subtracting this integral over here. What if I were to add that integral to both sides? Well, if I add this integral, which is the same as this integral, I'm really going to get 2 of these integrals over here. So this will be 2 integral e to the x sine x equals negative e to the x cosine x plus e to the x sine x, because I've added that integral to this side over here. So now I have 2 of them. Well, if I now want to solve for this integral, simply divide both sides by 2. So what I'm going to get is the integral of e to the x of e to the x sine of x dx is all of this divided by 2 plus c. A little bit of a pain, but overall not too bad. And ultimately, in a case like this, typically if you have 2 cyclical functions like this is the general idea of what's going to happen. You're going to end up with something where it takes a couple of cycles to get to your answer. In this case, it took 2 cycles, and I think that's pretty much the way it's usually going to work. It's going to take a couple of cycles to get back to getting this integral, which is the original integral. That's kind of what you're looking for, is we want to have this integral, which is the same as the original integral that we're solving for. Then we can add it over to this side and then divide by the coefficient. One thing I want to mention is maybe this e to the x right here is e to the 2x. So when you take its antiderivative, you'll end up with like a 1/2 out in front or something, because when you do a little u substitution there, you would get a 1/2. Well, that just means I'll be adding a half of that integral over to here, so I would get 3/2 of the integral. Well, then you just divide by 3/2 or multiply this whole thing by 2/3. So you may end up with coefficients out here, but that's okay. You're just going to add that coefficient of the integral over to this side. All right, hopefully that makes sense. Again, these are a little bit tedious, but this is what you're looking for. It is a relatively common integration by parts type problem. All right, last problem. So now we want to take the the integral of inverse tangent of x dx. This time it's got bounds, so from 0 to 1, this is a definite integral. We will not have a plus c. We'll have to do some evaluation at the end of this thing. So let's see, antiderivative of inverse tangent. Well, I know the derivative of inverse tangent, but I don't know the antiderivative off the top of my head. So this is an integration by parts. Fortunately, this is an inverse trig. So the first thing that we look for is log. There's no log, but inverse trig is the second thing. So u is inverse tangent of x. dv is everything left in this case, which is just dx. So du, and I did say we're going to have to make sure that we know this when this is going to start appearing a lot more. Derivative of inverse tangent is 1 over x squared plus 1, or 1 over 1 plus x squared dx. And then the antiderivative of dx is just going to be x. So this integral is uv minus the integral of v du. So uv is x inverse tangent of x minus the integral of v du, which is x over x squared plus 1 dx. And technically I should probably put that this is going to be evaluated from 0 to 1, and this is still evaluated from 0 to 1. I typically don't evaluate all this stuff until the very end. And the reason for that is because what's going to happen now. This one right here might look at it and say, well, I don't know how to undo this because we haven't talked about how to undo a quotient rule. Technically, you're right, but this is a technique that we've learned before. Sometimes, once you take integration by parts, whoops, too far, you end up with something where you might have to use a different antiderivative technique that we've already learned. This one, you can actually do a u substitution, or a standard substitution on this one. So this one, we can actually do a standard u sub on. So in this case, to evaluate this integral, u is going to be x squared plus 1. That's the most composited piece, right? The whole denominator is really to the -1, so it's composited. Remember, this is standard u substitution now, so just du is going to be 2x dx, and we'll need to solve that for dx. So dx is du over 2x. And that's going to give us a way to evaluate this one. So down here, let's see, we had x inverse tangent of x. That was evaluated from 0 to 1. The new integral is going to be minus the integral of x over u, because u is x squared plus 1, times my new dx, which is du over 2x. Notice I didn't put any bounds in here. You could change the bounds if you really wanted to. We can get rid of those x's, which is good because now everything's in terms of u. So we could change the bounds and just evaluate two different things. I prefer not to in this case. This is up to you. Just be really careful on it if you do. So we end up with x inverse tangent of x from 0 to 1 minus, now I'm going to pull the 1/2 to the front, and then I have the integral of 1 over u du. This one I can take the antiderivative of. So this is x inverse tangent of x from 0 to 1 minus 1/2. The antiderivative of 1 over u is the natural log, absolute value of u. No plus c, and I will evaluate this thing, but I'm not putting the bounds yet because I'm going to go ahead and go back to x. That way my whole thing is going to go from 0 to 1. So I get x inverse tangent of x minus 1/2 the natural log. The original u was x squared plus 1. You can put it in absolute value, but you don't need to because x squared plus 1 can never be 0 or negative, so that's okay. If you put the absolute value, it's not wrong. And that whole thing is going to be evaluated from 0 to 1 since I went back to terms of x. So now it just becomes evaluating this thing. So let's see what we get when we plug in 1. So we're going to get 1 times the inverse tangent of 1 minus 1/2 the natural log, plugging 1 in here. 1 squared plus 1 is 2. So that's the first one. Minus, plugging in 0, we get 0 times the inverse tangent of 0 minus 1/2 the natural log. Plugging in 0 here, we get the natural log of 1. And that's the second piece. Alright, so we need to go ahead and evaluate this thing now. So let's see, we do have to know our trig stuff. Inverse tangent of 1. Remember that tangent's inverse is limited from negative pi halves to pi halves, not including the endpoints. So the inverse tangent of 1 means tangent of what angle is going to give me 1? Well, that has to be at pi fourths. So 1 times pi fourths is pi fourths, minus 1/2 the natural log of 2. Okay, I don't know what the natural log of 2 is, so we're just going to leave it like that. 0 times inverse tangent of 0, well, inverse tangent of 0 is 0 anyway, but 0 times that would be gone, minus 1/2 the natural log of 1. Hopefully you guys remember this is one you need to know. The natural log of 1 is 0. So all of this right here is 0. So this right here technically is your final answer. And want to make sure that you guys understand this is perfectly acceptable. It could be written in a slightly different way. Properties of logs say that if I have a coefficient here, I can bring it up as the power of my argument right here. So technically this could be written as pi fourths minus the natural log of 2 to the 1/2 power, but of course a 1/2 power is a square root. So this also could be pi fourths minus the natural log of the square root of 2. Okay, it is quite possible that you would see the answer in either one of these two forms, and either one of them is perfectly acceptable. All right, there you go. So we kept that one to just under 20 minutes, like I was hoping. Both videos right around 20 minutes. So there you go, integration by parts.